In this video I will show you how to make this grass vertex shader step by step that allows the player to move freely in the grass and make it bend and move wherever the player are. This interaction is seen in games such as Zelda Breath of the Wild or Genshin Impact, and it gives a quite nice effect on the grass. It makes it look more alive. I will not implement wind in this video, but I will show you how to make the interaction work step by step. Let's begin, shall we? So, in order to create this grass, first we need a mesh. And I already have a mesh here. So let's open this mesh up. This mesh is basically just planes. But we need a material. So let's create the material. We're gonna call this material my grass blades. Let's open this up. So now the first thing we need to do is to change the shader model. So we're gonna change the shader model to masked, and we're gonna change the to two-sided foliage because we want to render the back side of each plane as well, and we're gonna apply two-sided. Right. Then we need to add some textures that I have here. Since it's a stylized grass, I don't have a normal map. I'm just gonna use the base color. I'm gonna use subsurface color. I'm gonna use the alpha for opacity mask. I'm just gonna use the red channel for roughness from this material texture. We're also going to add a scalar, and we're going to have metallic and specular to 0. Let's apply that. We can look at the preview how the grass blades are starting to appear. Now let's add this new material that we just created and apply it to the mesh. And this is how the mesh looks like now with the alpha alpha grass. Then we can take this mesh and apply it in the world. It's gonna look like this for now. And we can even multiply this, and we can rotate it a bit, and then we can multiply this again. So we can create this nice little patch of grass. And we're gonna rotate this again a bit, so. Right. So this is our beginning of our grass. We can even get our player. So you can stand here and be ready to move in the grass whenever we have all the information we need. We can even play, and then we can see that nothing happens when we move in the grass now. It's also important that we turn off collision. So no collision is important. Next step is, so now when we have the grass, and nothing happens in the grass. So this grass shader here that is connected to the mesh needs to know the location of the player in order to allow each grass blade to bend and move depending on where the player is. So in order for us to actually get the player position data to the shader, we need to create something that is called a material parameter collection, and we're gonna call this my player pos. This is this material collection is super useful to send data from blueprints to shaders. And then we're gonna create a vector parameter, and we're gonna name this vector player pos, and the default values are gonna be 0, 0, 0, because these values will be set by the blueprint later on. So now when we have created that, we save it, and we can go back here, and we can now see that we have this here. Now we need to open our third person character. So this is the blueprint. This is the blueprint for our third person character that comes default with Unreal Engine 5. We have the construction script here. We don't need it. And here's the view. Here's the viewport. I forgot to mention that, but this is like the default where we show the player. And here's the construction script. We don't need that right now. And then we have the event graph. This also comes default from Unreal Engine 5's third-person character demo, and we don't need to care about what happens here. The only thing we need to care about is the event tick, cause we want each tick. On each tick the player is active, we want to feed data to our material collection, so the shader can actually know the position at all times where the player is located. So in order to do this, we need to make a sequence, and this sequence will allow the other operation here to continue. But now I can sequence this, and I can actually call another node called vector parameter value. So this vector parameter value can be connected to this material collection we just created. And if we click on this button here, we can actually find the newly created material collection that we just created. We can add that there, and then we can take the actor location, and we can put this here. So this is converting a float 3 to a float 4, I think. Yeah. Well, because we have RGBA, but we just care about RGB because we just want position in X, Y, and Z. That's what happens here. We also need to add the parameter name that we just added here, player pos. And we can just find it by default here. And then we apply, we save and compile the code. So now this is done. So now each tick we send location data to this material collection, which is quite useful because now we can go to our shader. So now we're in the shader. Now we're gonna get our collection parameter, and it's already set to my player pos, and we're gonna call player pos. So this is now this node will get the player position each tick and feed it into here. So in default this is 0, 0, 0, 0, but depending on where the player is at runtime, this node will be updated. We also want to create a sphere mask now, and for that we need the absolute world position. And we need, since this is a float 4, we need to mask this out and just use RGBA, because this is a float 3 and this is a float 4, so we just want to convert this to a float 3. When we have that, we can subtract these two positions. And when we have subtracted these positions, we want to use a length, a vector length. So we put vector 3 length, so we get the length. And then we want to divide this with something we will call, so we will use a scalar, and this scalar is called, we will call the scalar effect radius. This will determine the radius of our sphere mask. And we can put this to default value of 80. And then we can use a power, but we will just put this to 1, the exponent 1 for now. And then we also want to saturate. A saturate node is basically a clamp node that clamps the value between 0 and 1, so we don't get weird results. And then after that, we want to invert it with a 1 minus. And then we don't see anything in the preview just yet. But the sphere mask math is now completed here. I will show you later what the sphere mask actually does. Okay. Now we want to trample the grass. So we want the grass to move down when we move in the grass. So in order to do that, we're gonna create a float 3. And in Unreal Engine, up and down is Z. Is in the Z axis, not Y axis, like in Maya, for example. So we're gonna create some static values because we know that we will never trample the grass in this function. We will not trample the grass down into the sides. We just want to trample the grass downwards. We call this. So we set X and Y to static values of 0 because that will have no effect. But we want to be able to adjust the trample effect in up and down, and that is in Z. So that's why we create this scalar called trample. And we can set the default value here to -40. Why I use scalars is that when we will create a material instance, and there we can adjust these values on the fly without having to change the master material, which is quite convenient. Now, when we have the float 3 that will determine how much we trample the grass, and then the sphere mask that determines the player position, we can now multiply this with this. And in order to demonstrate what this does is a good example. We might just take this and we might actually just put this in here, and we disconnect the subsurface color, and we can disconnect this and this, this and this. And we can use a plane. So this sphere mask here creates this black and white mask that can be used to determine where the player is located in the shader. So in this case we have 0, 0, 0. That's why we get this circle in the middle. But if we create a float 3, for example, and connect this here, and we have 0, 0, 0, we get it in the center. But if we, for example, move in R, that was quite a lot, maybe. Let's move a bit more. 50. No. Yeah, okay, so here we can see how the mask moves depending on the input of this. So you could view this float 3 as a static position of where the player is located, but we want it dynamic, and that's why we use this material parameter collection that is fed through the blueprint at all times. But this demonstrates what the sphere mask does, basically, because now we will have no effect where it's black, and we will have max effect when it's white, because white is 1 and black is 0. And if you multiply something with 0, you will get 0, and that is no effect. So this is what the sphere mask does. So we will always want to multiply stuff with the sphere mask in order to get effect. So we can even name this sphere mask. So here we will basically move the mesh vertices 40 units downwards where we have effect, and we will move nothing where it's black, because it would be, the minus 40 will be multiplied by 0, and that is 0. But 1 multiplied by minus 40 is minus 40. So we can connect this now to our world position offset. This is basically offsetting. This basically offsets the vertices. And we also, of course, want to reconnect all our values. Subsurface color, opacity mask, so roughness. Alright. Now we can take a look how it looks. So now we get this trample effect. If you remember from before, we had no effect, but now we trample the grass downwards by 40 units. Which is great, because something is happening. Now is a good time also to create a material instance, because we added the custom parameters that we can change in runtime. And I always use M for the master material and then MI for my material instances. And then we want to go back to the plane and change this here to MI, my grass blades. So now we have the material instance applied, and we can save it. And now we can even try to adjust. We can adjust the effect radius. For example, we can have 200 and we can trample the grass by 100 instead of 40. We can save this and we can go back here and we can see how it looks now. So now we trample the grass a lot more. But this gives us a lot of freedom to change however we want. It's a quite wavy effect, as you can see. Alright, so let's change back the values to minus 40 and 80 again, because that's more reasonable than that large radius. That works. So just having the grass move up and down it looks okay, but we can make the shader more interesting. And to make the shader more interesting, we actually could make it so that each grass blade bends to from the player position and then bends outwards, so we can get this like nice kind of circle around that the grass blades actually move away from the player when he approaches. Alright, so in order to create that, we take this subtraction between the world position and our player position that runs dynamically, and we multiply this with a float 3, and this float 3 is 1 in R and 1 in G, because that means that we will move in the directions around the player, so not in Z, so not up and down now it's just in the green and the red axis, as you can see here in this little gizmo. So now we want to determine the directionality, basically. And we do that by multiplying this, as I said. So we multiply in the direction we want, and then we also want to normalize this value so we don't get strange results, because we just want the directionality. And then we want to multiply this with another scalar parameter, not a static one, we want a scalar, and we're gonna call this bend. So this is how much, like the strength of the bend, and we will determine that to be 100 units. And after that, so now we have the directionality and we have the bend strength. Now if we would apply this, we would basically bend everything from top to bottom, and we don't really want that because that's not realistic. Grass actually bends like they are rooted in the ground, so we don't want to move them from the root of the ground. We just want to move the top, and then gradually decrease the movement towards the bottom. So in the bottom we want 0 effect because they're rooted, and in the top we want max effect. So we need some sort of gradient, and luckily gradients can be created using a texture coordinate. And we can mask that again with this very convenient component mask. Now we want not in this direction, but we want this direction. So then we remove the R channel and we just use the G channel, and we get this. We get this nice gradient. However, as I said, we want to multiply by 0 down here and 1 down up here. And as you can see, the black is in the top, which means that we need to invert this. And we invert this again with 1 minus. Now you can see that the gradient is going from 0 to 1 in the G channel. And this is perfect because this is exactly what we want. So now we can multiply this with our bend strength, and we get this. And then again, we don't want the grass to bend all over the place, so we want to multiply with our sphere mask again, so we only affect the area around the player, not everywhere. We could actually make it make a test here. We can actually add this right now, so I can show you how it will look like if we don't account for the masking of where the player is located. So as you can see, when we play, every single grass blade moves away from the player, which gives a quite cool effect, but it's not really what we want. We want the grass blades to just bend close by to the player, because that makes sense, right? Because the player has effect on the grass. So let's go back here and yet again multiply with our sphere mask. And now when we have this, now finally we can add it, and then we can keep the connection to world offset, and we can apply it, and there you have it. So the shader is now complete, and the grass is just moving around the player, and it looks quite effectful. I've seen other videos where they use sign distance fields or render targets, and that's quite expensive. I think a good approach is actually to use the player position, but you know, any technique works. But I like this technique a lot, actually, and I know other game developers actually use this technique. It's nothing revolutionary, but I think I've showed you step by step how to create this, and I'll hope you try it out for yourself in Unreal Engine 5. So yeah, thank you and bye.